Chalo, let us start with all our interhalogen compounds. Okay, we completed with the chlorine, okay, in the last lecture. Next, we are going to start with today is the hydrochloric acid. Okay, hydrochloric acid, or tell me one thing, hydrogen chloride. If I say hydrogen chloride, okay, hydrogen chloride. Is it a strong acid? Is it a strong base? It is a weak acid? Is it a weak base? What is it? Hydrogen chloride. What is it? Okay, Sarjana says strong acid. Good. What is hydrogen chloride, everyone? Is it a strong acid? Is it a weak acid? Is it a strong base? Is it a weak base? What is it? Strong acid. Okay, strong acid, strong acid. Yeah. And you know, this is the best feeling as a teacher when everyone gives the wrong answer. Okay, that means he or she has fallen into trap. Okay, that is the best feeling, I tell you. Okay, like whenever your teacher, even in the exam, you know, he might be giving you some trick question and he sees no, everyone has fallen into trap somewhere. After checking the paper, he must be doing yes, you know. I had laid the trap and everyone has fallen into trap. So what if I say hydrogen chloride is a weak acid? Will you believe me? Yeah. See, if it was so easy, okay, at hydrogen chloride, if I ask you HCl, and if it is strong acid, why will I ask you? Isn't it? Yeah. If the answer was so easy. See, hydrogen chloride. What is an acid? Tell me one thing. What is an acid? What is an acid? Yeah. What is an acid? How do you define an acid? Gives H plus easily, gives H plus easily. Perfect. Okay. Now hear this carefully. When I say hydrochloric acid, okay, this is different. Hydrochloric acid is different and hydrogen chloride is different. Now what is difference? Now HCl, which state of matter generally HCl present in at room temperature? Yeah, Sarchna and Sindhuja and Muldeep, HCl, which state of matter is there? Is it a liquid? Is it a solid? Is it a gas? And says liquid. Sarjana says liquid. Yes, everyone, come on, reply. Is it a liquid, solid, or gas? Liquid, liquid, liquid. Can we all agree liquid? Yeah? No. HCl is acid on room temperature. Okay. Pure hydrogen chloride. Oh, sorry, not acid. I want to say gas. Okay. Pure hydrogen chloride is gas at room temperature. Okay, hydrogen chloride is not a strong acid. Your hydrochloric acid, when do you get hydrochloric acid? When you dissolve this into aqueous medium. Okay, so in the aqueous medium, like, see, understand the logic. When you will get H plus, when you put it in the aqueous medium, no, if you do not put it in the aqueous medium, it will not give you H plus. Yeah, in the gas you have HCl gas, okay, a pure HCl gas. Do you get H plus from the gas directly? Yeah, no. So how we can say it is a strong acid? No, hydrogen chloride is not a strong acid. Okay, but hydrochloric acid, when you put that HCl, in the aqueous medium, that time it will become strong and it will dissociate, it will give you H plus. That time you can say HCl is a strong acid. So what you see at the laboratory is the liquid, that is hydrogen chloride dissolved in the aqueous medium. Are you getting it, everyone? Or you can liquefy it, obviously. Is it clear, everyone? The difference. Okay. So you have various oxidation state. We are going to look at this interhalogen compounds. Okay. So we have interhalogen compounds. We have HCl. So let us first start with the HCl. HCl. How do we prepare HCl? See, it is simple. Okay, we want to prepare HCl. As I told you, HCl is what? HCl is a, you can see over here, HCl is a gas. Okay, HCl, what you get, a pure HCl is a gas. Okay, so simple it is. So when I take sodium chloride, okay, like I'll take Na and Cl, okay, and I'll take a acid, okay, and I'll take another acid. Not HCl we want to prepare, I'll take another acid. So obviously what will happen? H plus Cl minus come together to give you acid. Simple as that. For example, if I treat it with H2SO4, yes, H2SO4 dissociate as what? In the first step, it dissociate as H plus and HSO4 minus, correct? So H2SO4 dissociate like this, NaCl dissociate like Na plus, Cl minus. So H plus, Cl minus come together to give you HCl, Na plus and HSO4 minus come together. And this continues again. If I treat it again, if I add sodium chloride, again it will dissociate one more H plus from this and it will again give you HCl. Come on, write this down. Just write down the reaction. Just write down the reaction. So when I heat acid and a sodium chloride, yeah, we get the HCl. We get the HCl gas. We get the HCl gas. I hope it is clear, everyone. Come on, write down those reactions. It can be done in the chat box. Come on, write down the reaction and done in the chat box. Done. Come on, done in the chat box. Only write down only two reactions. That's it. Okay. Write down only two reactions. And you should remember this. Okay, you should remember this. If I take salt and acid, what do I get? I'll get the HCl. Simple as that. Simple as that. Okay. Chalo. Let us go ahead. So as I told you, HCl, remember HCl, what is this? HCl is a gas and not liquid. I know why we say liquid, because in the laboratories we see it as liquid, isn't it? On the shelf, we never see HCl kept as a gas. Yeah, HCl is always kept as a liquid. We say hydrochloric acid. So when I say hydrochloric acid, at that time I consider it in the liquid state. But when I say hydrogen chloride, okay, that time I will say it is a gas. I hope the difference is clear. Okay, so do not get confused. If someone asks you, now you are a chemistry student, you should know this. Someone says hydrogen chloride, it is a gas. Someone says hydrochloric acid, it is a liquid. Simple as that. Now, obviously, as I told you, hydrogen chloride, will it be like a good soluble? How would be solubility? It will be a good soluble, or it will not be soluble in water. What do you think? Will it be a good soluble? Like solubility will be high, medium or low? What do you think? Yes, solubility will be high, medium or low. What do you think? In the water, the solubility of HCl will be high, medium or low? Yeah. Come on, tell me. Fine, even if it is wrong. Come on, try. Think about it. Think about it. There is a logic behind this. Okay. Either it will be high, either it will be low. But there is a logic behind it. Why and why it should be high? Yes. Solubility of HCl. Yes, Prashanti and Muldeep. Solubility of HCl. Sasidharan, will it be high, low? Bhuvnashri, Prashanti. High. Anthony, what will be? High. Okay. Intermolecular hydrogen bond. Okay. Yes, there exists an intermolecular hydrogen bond. What else? What is the famous dialogue? I always say that is useful in the biology also. Cl and O are both electronegative. Yes, there is an intermolecular. What else? What else? What else? HCl. Is it a polar or non-polar? Yes, Prashanti. HCl, Sindhuja. Is it polar or non-polar? Yeah, Ragul, HCl. Yes, correct. HCl is polar in nature. Yeah, and the line that I always say you have written down in the book also. What dissolves what? Yeah, what dissolves what? Your like dissolves like dissolves like HCl is polar in nature. Similarly, water, is it a polar or non-polar? Prashanti, Sindhuja, Anmoldeep, Bhuvneshri, your water, is it polar or non-polar? Correct? Even water is polar. So, yes, correct and correct, Prashanti. Like dissolves like. That means what? Water is polar, HCl is polar. Obviously, the it will be highly soluble in water. Okay. Pungent and suffocating smell. Okay. Aqueous solution, this is what I told you, Sarjana, that aqueous solution is called as hydrochloric acid. Okay. Heavier than air, easily liquefiable. Yeah. White crystalline solid if you freeze it, because it is colorless. Because it is colorless. Is it clear, everyone? Are the physical properties clear? Come on, give me yes or no. Are they clear? Come on, yes, yes in the chat box. Is it clear? Okay, fine. Sure. Okay. Let us go ahead. Action with litmus. Obviously, isn't it obvious? Blue litmus to red. What does that mean? Yeah. Have you ever seen the litmus paper? Rashida, Sarjana, Sashidharan. Have you ever seen the litmus paper? Yeah. I hope you have used it also. You know, even the pure litmus paper. Okay, pure pH paper. Okay, pure pH paper. It is also very costly. If you look at the pH paper, no, it is made up of strips. Okay, not the litmus paper. Okay, litmus paper is either, you know, it can be blue, red, or yellow, whatever you want. Okay, but your pH paper, they make lines like this. Just like you have thermometer, no, similarly you have a pH meter, pH1, pH2, pH3, pH4, like that, and it is costly. But litmus paper is not that costly. So what happens in litmus? If I turn blue litmus to red, what does that mean, Anthony, Sarjana, Anmoldeep? What does that mean? That means I have an acid. Correct? I have an acid. Okay? I have an acid. That is the meaning of that. Correct? Now, obviously, it behaves as one of the strongest acid, Ka 1 into 10 to the power 7. Now, remember, Ka is directly proportional to acidity. Will be useful for your equilibrium chapter. Ka directly proportional to the acidity. Okay, Ka is direct. Higher the Ka, higher the acidity. And pKa is opposite. Okay, do not get confused. pKa is opposite of Ka. Okay, so Ka, the higher the Ka, higher is the acidity. Okay, stronger acid, that means that Ka will be high. Simple as that. Okay, so it is obviously strongest acid. If you dissolve it in the liquid in water, it will dissociate, it will give you H plus. Okay. Now what will happen if you do the reaction? Simple. Okay, like I have Na, I have HCl. If I react hydrochloric acid with sodium, what will happen? Yes, obviously chlorine and sodium come together to give you NaCl, hydrogen gas is released. Again, zinc takes the chlorine, hydrogen gas release. Magnesium takes the chlorine, hydrogen gas release, hydrogen gas release, hydrogen gas release. Simple as that. So stable state, you have to write it down. Simple. Okay, do not make it complicated. Simple. Okay, so write down two reaction from this. Any two reaction from reaction with metal. All of them, remember, all of them, if you react it with metal, they will eventually, what they will give you? They will give you hydrogen gas. All of them will eventually give you hydrogen gas. Okay, and hydrogen gas is explosive in nature, isn't it? Last time I remember someone told me that in our balloon, yeah, the balloon which is lighter than the air, the balloon which goes up, we feel hydrogen in it, is it? We feel helium in it. We feel helium, correct? We feel helium. Come on, write down the two reaction and tell me done in the chat box. Done. Okay. Sure. Let us go ahead. Let us go ahead. Okay. Then obviously oxidation. Oxidation means over here what is happening. If I have HCl, if I react it with oxygen, simple as that. I have hydrogen, I have oxygen. If I combine, only one product is possible, that is water, and chlorine gas is released. Now, reducing agent, come on, in the chat box, quickly. What is reducing agent, Sashidharan? Come on in the chat box quickly. And Sarjana, Prashanti, what is reducing agent? And Muldeep, I am saying reducing agent. Correct? Correct, Sarjana? Correct. And I am talking about reducing agent. Reducing agent. Reducing agents. Reducing agents. Yeah, what are reducing agent? Yes? Correct, Sashidharan. So reducing agent. Agent is the one which does your work, isn't it? Same, reducing agent. So it reduces the other but undergoes itself oxidation. For example, over here, come on, quickly calculate MnO2. What is the oxidation state of Mn over here? Yes. What is the oxidation state of Mn over here? Quickly. MnO2. Oxidation state of Mn. Correct. And come on, quickly, quickly. Correct, Bhuvaneshri. Correct, Sashidharan. Yes, Prashanti, what will be the oxidation state? Correct, and Moldeep. So I have plus 4 oxidation state. I have plus 4 oxidation state. Now, MnO2 to MnCl2. MnCl2, what is the oxidation state of Mn in MnCl2? Yes, Sashidharan, quickly. MnCl2, what will be the oxidation state of Mn? Yeah, correct? Plus 2, plus 2, plus 2, plus 2, plus 2. Correct. So plus 4 to plus 2, Anmoldeep, Sarjana, what is this? Is it oxidation or is it reduction? Yeah, perfect. It is nothing but your reduction. So your MnO2, yes, correct, Sashidharan, correct, Anmoldeep. Your MnO2 is undergoing reduction, and what is happening over here? You are getting MnCl2. So who is doing the reduction? Your HCl is responsible for the reduction. Hence, we call it as a reducing agent. Same case over here, KMnO4. Come on, quickly. What is the oxidation state of Mn over here? KMnO4. What is the oxidation state of Mn? Yeah. What is the oxidation state of Mn in KMnO4? Sashidharan, Sindhuja. Yes, Ragul. What is the oxidation state? Anthony. Correct. And yes, everyone, come on in the chat box. What is the oxidation state of Mn? Correct, Sashidharan. Yes, I'm waiting for answers, everyone. What is the oxidation state of Mn in KMnO4? Yes, Prashanti. Correct, Sajna. Yes, Sindhuja. Bhuvaneshri. What will be the oxidation state? Anmoldeep, is it 3? No. Do it again, Anmoldeep. Oxygen is not -1. Please remember that. Is oxygen -1? Yes. Kirtini, what will be the oxidation state of Mn? Yes, Ragul. What is the charge on oxygen? The charge on oxygen is -2, not -1. Yeah. So K is +1, Mn is X, oxygen is -2. So I'll write 4 into -2 is equal to 0. So if you solve this, X 1 plus X -8 is equal to 0. X is equal to -8 goes that side, +8 +1 goes that side, -1. So +7. So Mn is +7. So KMnO4 to MnCl2. Again, MnCl2. That means +2. So +7 to +2. Is it oxidation or reduction? Bhuvaneshri. Yes, Ragul. +7 to +2. Look over here, Ragul. So +7 to +2. Again, it is reduction. Correct. So who is responsible? Your hydrogen chloride is responsible. So MnO2 undergoing reduction, correct, Anthony. KMnO4 undergoes reduction. K2Cr2O7 will also undergo reduction. And who is responsible? Your hydrogen chloride is responsible. Hence, your hydrogen chloride is acting as a reducing agent. Is it clear, everyone? Okay. Now look at the next reaction. HCl plus F2. Okay. HCl plus F2 is giving me HF. Okay. Now over here, everyone, if I react, if I do the opposite, okay, if I do the opposite, like, or let us say if I react HBr plus I2, will reaction happen? Come on, tell me. HBr plus I2 or HCl plus Br2, will the reaction happen? Or HCl plus Br2, will the reaction happen? Will I get HI and HBr? Come on, give me yes or no. Yes or no? What do you think? Will the reaction happen? If I react HBr and I2 and HCl and Br2. Come on, I want yes or no in the chat box. Will the reaction happen? No, answer is no. Sasitaran says no. Why? Yes, Sanboldeep. Why will it not happen, Sasitaran? Why will not it happen? HBr plus I2, HCl plus Br2. Why it will not happen? Yeah. Why it will not happen? Stability, correct. So it will be not able to replace. Yes, correct, Sajna, but that is what I'm asking. Why? Cl is more reactive than Br, so Br cannot displace Cl. Perfect. So as we go down the group, we have seen it in the last session, and Moldeep, as we go down the group, yes, the reactivity decreases. F2 is more reactive than Cl2, then Br2, then I2. Correct? So your Cl can replace F, correct? Is it? No, it is opposite. Your F can displace Cl. Your Cl can displace Br, but opposite cannot happen. Cl is more reactive. Your Br is less reactive. Similarly, iodine is less reactive. Br is more reactive. Correct? Hence, it cannot displace, so this reaction will not happen. Is it clear? Is it clear, Aragul, Anmoldeep? Is it clear? Okay, chalo. Let us go ahead. Okay. Now further reactions, simple. Okay. How many of you have seen? Have you ever like seen the Eno? Yeah. What do we call it? Eno. Have you ever seen the ad of Eno? Yeah. Eno. Anyone seen it? Eno or heard about it? Eno. Yeah. Unmold it. When do we take Eno? Anyone else? Yeah. When do we take Eno? Yes. Okay. Very good, Anthony. Yes, Ragul. When do we take Eno? Acidity. Correct. For acidity. Yes, we all know for acidity. So obviously, Eno must be what? Yeah. What must be Eno? Obviously, it is a base. Okay. Now, it is in the ad also. It is in the ad also. When we take Eno, after 6 seconds, immediately, what do we do? Yeah. After 6 seconds. Yeah. Immediately, what do we do? Anmoldeep, Ragul, have you ever seen, correct? Yeah, we do what our grandparents and parents do after eating a good dinner, isn't it? They burp so loud. Oh my God. At least we burp it like, okay. Our grandparents and parents, how do they burp? Prashansi, yeah. How do they burp? Yeah, they burp like, oh, yeah. Like whole colony, whole building wants to know what have you ate for your dinner. Yeah, they burp it like this, isn't it, Ragul? Yeah, they burp like the whole colony wants to know. Oh, today I had paratha. Today I had butter chicken. Yeah, today I had a good biryani. So whole colony should know. So why do we burp? Huh? Why do we burp when we take Eno? Yes, Anmoldeep, why do we burp? Even if you try to control it, you cannot. Okay, like that burp will come no matter what you do. Why? Yeah, why do we burp? Yes, Ragul, have you ever thought? Like they say, you will burp in 6 seconds. They are so confident. Yeah, someone can sue them. Yeah, I have taken Eno and I did not burp. So we can sue them in the court. But no one can because you are going to burp. Why? Yeah, Anmoldeep, Ragul, Sajna, Anthony. Yeah, why do you burp when you take Eno? Yes, correct. And but what? Which one? Yeah, why do we burp? Because in your eno which is base, it all are carbonate base. Okay, these all are carbonate base. Now if you notice over here, sodium bicarbonate, potassium carbonate, what is common? Yeah, what is common? The carbon dioxide gas. So no matter what you do, when you take eno, this gas is going to get produced, and now that is searching from where should I come out. But luckily, it only comes out from our mouth. Yeah. Imagine you are taking eno, and after every 6 seconds. But so what happens? Your carbon dioxide gas gets produced and molded, and you burp. It comes out up from your mouth. You cannot control it. What you cannot, can you control carbon dioxide not coming out from your mouth? No, we cannot. Okay. Maximum we can do is we control it and we do not burp it from mouth, but from our nose. Oh my God, it will feel so, so bad. It feels horrible. Yeah. But yeah, why do we burp? Because the carbon dioxide gas is there. Okay, so that is what happening over here. Your carbonate base, then you react with acid like HCl. What will you get? Salt, water, and carbon dioxide. So acid plus base. What type of reaction is this? Anmoldeep, Ragul, and Sarjana. What type of reaction is this? Sashidharan, Bhuvneshri, Prashansi. Acid plus base. Correct? It is nothing but your neutralization reaction. Acid plus base gives you salt, and water is your neutralization reaction. Simple. So if you have carbonates, carbon dioxide will come out. If you have sulfates, sulfur dioxide will come out. If you have nitrate, your nitrogen dioxide will come out. Simple as that. Okay, so remember this. So when you put acid, some or other gas is going to come out. If it is carbonate, carbon dioxide. If it's sulfate, sulfur dioxide. If it's nitrate, nitrogen dioxide. Simple as that. Okay, and that can come in the exam. Which gas will come out from this reaction? This question can come. This question can. Okay. Then reaction with metal salts, again the same thing. Anmoldeep, if I react it with metal, I'll get the chlorides. Yes, simple. Again, Ag, if I react it with our HCl, metal with HCl, I'll get the chloride. Yeah, and the H plus will be released. H plus will be released. Simple as that. Same reaction. Okay. Aqua regia. Yeah. What is aqua regia? Anyone has prepared it? Aqua regia. Anyone has heard about it? I've told you a story about aqua regia, isn't it? Did I? Aqua regia. We remember aqua regia dissolves gold. But why? Why should it dissolve gold? Yeah? Aqua regia is very strong. Why it is very strong? Because aqua regia is a mixture of 3:1 acid. That is 3 moles of, not moles, 3 parts of HCl. If I take 4 ml, in that 3 ml will be HCl, 1 ml will be HNO3. So it are mixing with the strong acid HCl and HNO3. Okay. So I told you about aqua regia, isn't it? Like it fell on my shoe, okay, and my shoe was made up of cloth, okay, and it fell on the shoe, and what happened that I could see from both the ends. Okay, luckily my feet did not got hurt, okay, but there was a big hole in my shoe. Okay, so aqua regia, what we do, we add, rise down 3:1 rice, 3:1 HCl, HNO3. This is what, Anmoldeep, this is your aqua regia. This is your aqua regia. is 1 HCl and HL. Okay. 1 HCl and HL. Okay. So this is your aqua 3 and this is your nicyl chloride. So what happens when you make HCl and HNO3? Why it becomes so strong? Because you get nicyl chloride and you get the nascent chloride. Okay, that is the reason it dissolves gold. That is the reason, and it dissolves gold. Why? Because due to this nascent chloride, that nascent chloride reacts with the gold and makes it as gold salt, which is soluble. Okay, it makes gold salt is HCl, which is soluble. That is the reason your gold is dissolved in aquaria. What happens? Nitrosyl chloride is formed and nascent chloride comes out. Nascent chloride reacts with gold, makes it gold salt, which is soluble. Is it clear, everyone? Come on, give me yes or no. Is it clear? Is it clear? Okay. Now write down this reaction. Write down 1 and 2. Write down both the reaction. What is aqua regia? Write down the reaction. And probably 2 more lectures. Yeah. Then our P block we will finish. Okay. In next lecture we'll complete the P block probably, and the last lecture. Okay. I am keeping an extra lecture before our assessment. I want you to revise and come in that session. We will only discuss questions. Okay, I'm not able to take much questions of this chapter. Okay, so last session will be only questions. Okay, I want you to revise from the beginning, at least read and come, so that we will solve each and every question of your NEET. Okay, from all the groups. Okay, all the groups in 15, 16, 17, 18. Come on, write down both the reaction and done in the chat box. Done. Okay, sure. Let us go ahead. Now, hydrogen chloride uses. So, where do we use this? You know, yesterday in the JE class, one student gave me a funny answer. Okay, it is used in the tanning industry. What is tanning industry? Yeah, what is tanning industry? What is tanning industry, everyone? What do we mean by tanning industry? Yeah? What do we mean by tanning industry? Come on, Sashidharan, Anmoldeep, Sarjana and Anthony. What is tanning industry? Yeah? Sindhuja, Ragul?
So don't know exactly, but tanning industry refers for making fabric from animal sources.
Okay. You know, yes, it is correct. Okay, it is like the leather. Okay, the leather that they take it. Okay, the leather industry. Correct. So, like we use the leather. Correct. So, the leather that we take it from animal. Okay, the skin that we take, we convert it in the usable leather. Okay, that is a tanning industry. You can see over here. I have put some leather photos. Okay, which does not look like a leather, but it is a leather industry. Okay, you know, one of the students told me, sir, we use it to become dark. We use it when we go to the beach. Yeah. So he meant that there are tanning creams. Okay, the foreigners who are, you know, whose skin is very white. Okay, not even like fair. I am saying white. Okay, those white people use this creams that make them tan, that make them little bit brown, and then they go in the sun and they sit on the beach. Okay, so one student told me that he thought that tanning industry means that. Okay, so your tanning industry is not that. So I asked him, will you apply HCl on your face and sit in the sun? He was like, no. So so tanning industry is not something what we use it on our face and skin and then we go and sit in the beach. Yeah, no, that is different. Tanning industry is a leather industry. We convert our animal skin into usable leather. Okay. Then in cleaning metallic surface, obviously it is a strong acid, so we clean metallic surfaces, electroplating, cleaning, and all those. Okay. Then in manufacture of chlorides and chlorine, obviously chlorides means NaCl, correct? We can use it. Then in manufacturing of glucose, in the preparation of aqua regia, and this line you can use it for every chemical. It is an important reagent in the laboratory, yeah, that we throw directly in the sink, isn't it? Hmm? That we directly throw in the sink, which should not happen, but yeah, it is an important reagent in the laboratory and it is used in the medicines also. Okay, so these were your simple uses. Now let us go to the oxidation states of oxo acids. Now what are these oxo acids? As the name suggests, acids which will contain oxygen. Okay, so these are your oxo acids of halogen. Now these are little bit different from your normal acid in terms of stability. I'll come to that. But look over here. So your oxo acids of halogen. So you can see over here oxygen, 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 oxygen. Everywhere there is oxygen. So acids that contain oxygen as well as halogen. Simple as that. Okay. Now if your oxidation state is +1, we call it as hypohalous acid. Okay, hypohalous acid. Now halous means what? Halous stands for unmolded, it stands for halogen. So it will be fluorous, bromous, chlorous, and iodous. Okay, remember like this. +1 is hypohalous, so it is hypofluorous, hypochlorous, hypobromous, hypoiodous. +3, which is shown only by chlorine. Okay, so it is chlorous, that we call it as halous. Okay, the +1 is hypohalous, +3 is halous. Okay, so we say chlorous, bromous, iodous, but only chlorine exists in +3. Then we have +5, which is called as halic. Okay, so we had hypohalous, we had halous, then we have halic. So halic means chloric, bromic, iodic. Then we have +7, which is called as perhalic. Again, halic stands for halogen. So perchloric, perbromic, periodic. Is it clear, everyone? Come on, give me yes or no. Is it clear?
Sir,
Okay. So if you notice, fluorine.
sir,
Yes, Anthony.
sir, can you explain +3 and +5 again, sir?
Yes, I am coming to that. I'll take the example. Okay. So look over here, everyone. So when it is +1, Anthony, we say hypohalous. Okay. +1, how do we calculate? Is HClO. If you do not know how to calculate, I am talking about chlorine, unmolded. So chlorine, I'll take it as X. This is +1. Yeah. This is -2 is equal to 0. So X is equal to -2 goes that side, +1 goes that side, it is +1. Okay. So if it is +1, we call it as what? Hypohalous acid. We call it hypohalous acid. So halous means halogen. So it will be fluorous, bromous, iodous. Similarly, Anthony, if it is +3, if we calculate HClO2, it will be +3. So +3 we say halous, that means chlorous. Similarly, +5 we say halic, that means chloric, bromic, iodic. +7, Anthony, we say perhalic. That means I will say if I have chlorine, I will say perchloric. If I have bromine, I will say perbromic. And if I have iodine, I'll say periodic. Okay. So these are your oxidation states of oxo acids of halogen. Now it is noteworthy that fluorine only exists in +1. If you notice, yes, write it down, the exception kind of thing. Fluorine only exists in oxo acids of halogen. Fluorine only exists in the +1. Fluorine only exists in +1. No +3, no +5, no +7. Okay, fluorine only exists in +1. Similarly, +3, you have only one element or one acid, that is chlorous. So +3, you have only one element, that is chlorine. Okay, fluorine is only present in +1, and in +3, only chlorine is present. Okay, come on. Write down this chlorine plus 1 plus 3 chlorine exceptions. Write it down. Do not write all in this first column. Hypohalous acid if it is plus 1. Plus 3 only halous acid. Plus 5 halic. Plus 7 perhalic. Just write down this. That's it. Just write down the first column. First two columns. Come on. Come on, write it down and done in the chat box. Come on, done in the chat box, everyone, and it's done. Come on, everyone, done in the chat box. Done. Okay. The time it is 8:01. So we have already taken a break in the beginning. Not a break, but we wasted a little bit. Not wasted, but we have used little bit of time in the beginning. Okay. So chalo, it is 8:02. Let us take a break. Okay, we'll continue at 8:10. Okay. We'll continue at 8:10. Do not leave the session. Okay. Come back sharp at 8:10.
Sir, last slide, sir, please.
Yes, is everyone back? Come on, back in the chat box, turn on your cameras. Come on, turn on your cameras, everyone. Back in the chat box. Chalo, let us start. Everyone, let us start. So we have discussed this one thing before also. Like if I have HF and Sarjana, always give me wrong answer. If I have HF, HCl, HBr and HI. Sarjana, which is the strongest acid out of this. Yeah, which is the strongest acid out of this. Yeah. See, again, which is the strongest acid in this? Yeah, Sindhuja, Prashanti, Sashidharan, which is the strongest acid among this? HF, HCl, HBr, HI, which is strongest? It is HI. Sarjana, this is the third time you are telling me this answer, HF. It is the HI. It is the HI. Okay, remember, it is the HI. Okay. HI. Why HI, Sarjana? Because the size of H, forget about electronegativity. Electronegativity you will compare when there is a comparable size. Okay, over here you have only hydrogen and you have iodine. It is like having the ant and the elephant. Yeah? Can your ant hold elephant? Can it? No, you cannot. So it will break easily. That's why HI is the strongest. But, but, when we come to oxoacids, that is not the case. Now you do not have only hydrogen and halogen, you have oxygen also. Your hydrogen is not attached to halogen anymore. It is attached to the oxygen, which is attached to halogen. So over here, it is opposite. Over here, we will look at the electronegativity. Okay, so that's why HClO is the stronger acid than HBrO than HIO. Come on, write this down. Write this down. Come on, everyone. Important. Okay, and as I increase the electronegative elements, my acidity, not my acidity, okay, my acidity is in control. The molecules acidity, yes, they will also increase. So write down this as we go down the group. Yes, over here, as I am increasing the oxygen, the electronegativity increases, the acidity increases. So HClO is the weakest, then you have O2, then you have O3, and the strongest is O4. And over here, your chlorine is the strongest, then the bromine, and the least is iodine. Okay? Is it clear, everyone? Come on, write down this two acid character and tell me down in the chat box. Quick. Come on, write it down and done in the chat box. Okay, done. Okay. Then we have the oxoacids of halogen. Okay, then we have the oxoacids of halogen. Okay, the acidic character. Now, just now we discussed. Yes, your Cl, O4, O3, O4 will be highest, then O3, then O2, then O. Okay. Now there has to be reason why it is highest. Obviously, yeah, there has to be reason. There shouldn't be any only oxygen reason should not be there. There should be one more reason, and that reason is, if you look over here, as I increase the oxygen, what is happening? Yeah, if I increase the oxygen, yeah, when the H plus goes away, there is a negative charge on the chlorine. Yeah, there is a negative charge on the chlorine, and As the oxygens are more, Sashidharan, as the oxygen are more, what is happening? That negative charge can undergo resonance at the 4 different structure. Yeah, that negative charge can go under resonance at 4 different oxygen. So more the resonance, more the stability, more the acidity. Yes, resonance increases the stability. Okay, more the resonance, more the stability, more will be the acidity in this case. Is it clear, everyone? Yeah, is it clear? So if I have more oxygen, obviously there will be more resonance. Hence, H plus goes away easily. H plus goes away easily. Yeah, because H plus knows if I go away and if I give a negative charge to chlorine, that will undergo 4 times resonance. Yeah, so that's why H plus goes away easily. HClO4 is your strong acid than O3, O2, and O. Chalo, let us go ahead. Now let us talk about, I hope oxo acids is clear. Everyone, come on, give me yes or no in the chat box. Oxo acids are clear. Yes. Oxo acids are clear. Come on, give me yes or no. Okay. Okay. Sure. Now let us move to interhalogen compounds. Little bit of interhalogen compounds we looked at in the last lecture. Okay. Now interhalogen compound, that means what? There is a bonding between itself. Yeah. There is a bonding, Ragul. There is a bonding between itself. Like for example, halogen reacts with itself. Halogen reacts with itself. Correct. So I have interhalogen compounds like X, X dash, X dash thrice, X dash 5 times, X dash 7 times. Now, what is the main scenario? What is the main thing over here? That your X dash, the poly atom that you are forming. For example, I have IF5, I have IF7. So poly atom that you are forming should be small atom, correct? And this F5, F7, your F is smaller. Obviously, isn't it logical? Can I form Fi5? Like one large person, one strong person can hold 5 kids. Yeah, can hold 5 kids in the hand. But one small kid, can he hold 5 big muscular man? Is it? Is it possible? Yeah. Unless until that kid is a superhero. Yeah. So it is possible, but that is not the case. That will be exception case. We do not have any exception over here, luckily. So remember this, the poly atom, the multiple number of atom, what you have, F5, F7, that should be the smaller atom. This Fi5 is not possible. Is it clear, everyone? Is it clear? So we know what are interhalogens, compound with 2 or more halogen. Yes, and this is also one more thing. X is more electropositive than X dash. It is another way of putting it. Yeah, it is another way of putting it. Like X, that means the larger atom will always be more electropositive, because as we go down the group, electronegativity decreases. So it is another way of putting it down, that L positive than X dash. So it is, you can remember it from the size also, no issue. Okay. Now look at this. Look at this. Oh my God, there are so many molecules. Oh, how do we do it? Yeah. There is one thing I remember, like, obviously I had many friends from south of India. Okay. They used to always use this word da in the end. Da. Yeah. Haven't they? Or, when there is a casual talk, they used to say, I forgot it. Bachi, bachi, whatever. What? There was some particular word they used to say. What was it? Machi. Correct. Correct. I remember it. Yesterday I was talking to my friend, one of my friends, okay, from south of India. He was using this word. I remember it. Okay. So this many compounds, how many compounds we should remember? Yeah. So over here, you do not have to remember. It is logical. See, X dash is the smaller atom. Okay, X is the larger atom. So we have this many compound. Now look over here. IF. IF is not if. Okay, IF is not if. I is iodine, F is fluorine. So how to name this? How to name this? So the first atom that you have, for example, if I have ClF. So the first atom you have, presence P, you will write down the name of that, the name of the element. Cl is nothing but chlorine, and the second element you will add the ide. You will add the ide. Okay. So this is chlorine fluoride. Chlorine fluoride. So if I have BRF, it will be bromine fluoride. Okay. If I have IF, it will be iodine fluoride. So first element you will write down the element name, and the second element you will add the ide into it. Okay. Everywhere. For example, if I have ClF3, this one. Okay. So it is chlorine trifluoride. So first name as it is present C, Cl is chlorine, F I'll add ide. So chlorine trifluoride. Similarly, if I have BF5, okay, BF5. So it will be, it should not be BF, so sorry, it should be BRF5. Yeah, it should be BRF5. So it will be bromine pentafluoride. Bromine pentafluoride. Is it clear, everyone? Is it clear? Is it clear? Okay. Now remember this. Which of this following compound exists? Now, whenever there is a comparable electronegativity, okay, the electronegativity difference should not be high. For example, IF does not exist. IF does not exist. One thing is size. Fluorine is very strong. Iodine is very large. The fluorine is the most electronegative element, and iodine is also electronegative, but not as electronegative as fluorine. So the difference is very high. So when the electronegativity difference is high, the compound does not exist. Okay, the compound does not exist. Okay, so XX7 generally only one compound is there, that is IF7. Okay, XX dash mostly all compound exist except IF. Okay, IF does not exist. Like it exists, but it is very unstable. It is very unstable. Okay. Is it clear till over here? Come on, give me a yes or no in the chat box. Is it clear? Is it clear, everyone?
Sir,
Yeah, Sashidharan?
sir, I'm speaking of their like physical state.
Hmm.
You can see uh, like bro- bromine fluoride is a gas. Also,
Bromine?
fluoride X6
Ah, okay,
is a gas.
okay,
Also, bromine chloride is a gas.
okay.
But iodine bromide is a solid.
Okay,
Also, if we see bromine trifluoride, it is a liquid, and bromine pentafluoride is a liquid.
okay.
So, bromine generally is a liquid nonmetal. So,
Hmm.
bromine trifluoride and bromine pentafluoride being liquid is
Hmm.
not a thing, sir. But
Ha. Hmm.
why bromine fluoride and bromine chloride are gas,
Hmm.
whereas iodine bromide is black solid.
Okay. See, look over here. What is a gas? Okay, first of all, gas means you have a small particles, okay, which are randomly moving, correct? As you go down the periodic table, yes, and presence key, as you go down the periodic table, fluorine, chlorine, bromine, iodine, fluorine and chlorine, okay, fluorine and chlorine, what are they? Are they gas, liquid, solid? What are they, Sashidharan? Fluorine, chlorine are
So
nothing but
iodine is solid,
wow.
bromine is liquid, fluorine
Correct.
and chlorine are gases.
Perfect. So fluorine and chlorine is gas, bromine is liquid, okay, and iodine, okay, is solid. So what happens, when you go down the group, the size and everything increases. Okay. So over here you will also notice that as the molecules are becoming larger, over here also we are going from gas to solid. Okay. So over here also, as the molecules are becoming larger generally, okay, for example, iodine bromide, okay, iodine bromide, iodine is also large, bromine is also large. So iodine has its effect on it. Okay, iodine has its effect on it. So that is the reason your iodine bromide, wherever you will find iodine, generally saying, okay, iodine bromide both are of large size, it is generally of solid. While if I go with iodine and fluorine, okay, now there is a size difference. Okay, both are not almost comparable. Okay, fluorine is very small. Okay, so whenever I will have iodine fluoride, okay, so iodine fluoride, for example, look at iodine pentafluoride, iodine heptafluoride, yeah, even your iodine F3, okay, this also does not exist much, but so IF5, IF7, generally they are gas. So you can think about it like as the size of both the molecules are increasing, it is going towards solid. Okay, but if the size is very small, generally speaking, if there are too many fluorine molecules which is already gas, so it will be gas. So roughly you can extrapolate it, but there is no hard and fast rule. Okay, this size is large, then it should be only solid. But you can extrapolate it just for the understanding purpose. Otherwise, there is no such reason for it. If we want, like, if we go into further reason, then why it is solid? Obviously, if I attach IBr together, the molecules will be very close. So it shows the solid property. That's why it is solid. But if you want to remember, if you want to extrapolate, you can remember it like this. As the size is going on increasing, we are going from gas to solid. So you can consider iodine bromine large in size. They are solid. Is it clear, Sasidharan? Is it clear, everyone? Come on,
Yes.
give me a yes or no.
So, so both iodine and bromine are having larger size, so they are forming
Yes.
solid.
Yes.
So, but in the
Okay.
case of bromine fluoride, bromine is large in size, but fluorine is
That is
small in
what I am
size.
saying. No, where, like, if you notice, find out the fluorides which are solids. Can you find it out?
No, sir.
No. Correct. So that is what I am telling you. If you have fluorine in your molecule, generally speaking, they will all be gas. Okay. But again, as I am telling you, there is no hard and fast rule that due to size they are gas. They are gas because they show the gaseous property. Okay. That is why the reason they are gas. Okay.
Okay, sir.
Is it clear,
So this
everyone?
also comes true for chlorine also.
Chlorine? Chlorine? What chlorine? The pure chlorine you are talking about, or the interhalogen compound?
Yes, sir. Like you said, no,
Ah,
sir, all fluorides will not be in any fluoride will not be in solid state,
yeah,
either gas or solid state.
every fluoride, it will be either in gas or in liquid also. I don't think so there is any fluoride which is, except you have BrF3, okay, which is liquid. But generally fluorine are in the gas state. Even you can compare it with chlorine. Even chlorine also, generally, if it is with fluorine or with bromine, it will be in the gas. So the iodine, for example, ICl, again it will be solid due to iodine.
Yes,
Getting it,
yes, sir.
Sasidharan? Okay. Sure. So this is how you name your compound. The important part is this is how you name your compound. Okay. So first element you will write down the name, element name, and the second element we will add IDE. If it is fluorine, it becomes fluoride. If it is bromine, it becomes bromide. Chlorine becomes chloride. Iodine becomes iodide. Is it clear, everyone? Come on, give me a yes or no in the chat box. Is it clear? Okay, then there is a formation of ions also, not important. Okay, let us come to reaction. Just a minute, everyone. Just give me a minute. Okay, so let us do the reaction preparation. How do we prepare it? Sir, are these compounds polar or not? Yes, the compounds are polar. Why? Why the compounds are polar? Like, what is the main thing for polarity? How do we say it is polar or non-polar? We say it, and Sasitaran, how do we say it? Something is polar. Main thing is the electronegativity difference. Correct? The electronegativity
Dissociate
difference.
into ions.
Yes, Sasitaran, what happened?
Easily dissociate into ions.
It's dissociate. Why does it dissociate into ion? Like,
Because
if you forcefully dissociate, everything can dissociate into ion.
because in a
Ah,
polar compound, one molecule, like one atom or
atom.
thing, is more electronegative than the other.
Perfect.
So
Perfect. So, due to electronegativity difference, we say something is polar or no. So, although there are two halogens, but the electronegativity difference is high. especially compounds containing iodine and fluorine. Okay, high electronegativity difference. Yes, they are polar in nature. Okay, they are polar in nature. Okay. Now let us go to the preparation. How do we prepare it? Now we have done this little bit in the last lecture also, that if I take the equal volume of halogens, what will happen? I will get 1:1 ratio. That compound, for example, if I take chlorine and fluorine equal, I will get ClF. How do we say ClF? Come on, tell me now. Just now I explained you. How will you name ClF? Yes, Prashanti and Rajna. How do you name ClF? Kirtini, Sasidaran, Gopinath. Correct? How do you name it? Yeah. So we name it as correct. And yes, everyone, I want to answer from everyone. How will I name ClF? Correct? Chlorine, fluoride. So if I take the equal volume, I will get the chlorine, fluoride. If I take fluorine in excess, obviously I will get chlorine, trifluoride. Simple as that. Okay. And if I further react ClF with more fluorine, again I'll get chlorine trifluoride. Yeah. And if I further react chlorine trifluoride, I will get the chlorine pentafluoride. Sorry, I will get the chlorine pentafluoride. Same case with almost everyone. Same case with almost everyone. Look over here. Iodine, chlorine, almost in the equimolar. So I will have ICl. Iodine, chlorine, chlorine in excess, I will find ICl3. Same case with almost each and every interhalogen compound, and that is how you should also remember. That is how you should also remember. Okay. So these are some of the reactions that you should remember. Then this one. Now interhalogen compound, it is not necessary that I will react only halogen with halogen. Okay. There is another way of creating interhalogen compound. There is another way of preparing interhalogen compound. So they are prepared from halides. For example, if I have potassium bromide, KBr salt, yeah, and I react with fluorine, obviously potassium, it will have more affinity towards fluorine or bromine. Everyone, Sasidaran and Sarjna, potassium will have affinity towards fluorine more or bromine more. Yeah, will it have affinity towards fluoride or bromide? Obviously, potassium is positive. It will have more affinity towards the element which is more negative. Correct. So we have the most electronegative element, that is fluorine, with us. So obviously it will have more affinity towards fluorine. So what will happen? Your fluorine will kick out the bromine, yeah, and it will form KF. But some of the fluorine will react. Fluorine is a gas. Will react with the bromine which you have kicked out, and will form BrF. Okay. So interhalogen compounds not only form by reacting halogen with halogen, it can form by reacting halides and halogen. Okay, remember this. Write down this both the reactions. Same case over here. Ki and F2. Now obviously fluorine has more affinity towards potassium than iodine. So fluorine will kick out the iodine. Iodine which is released again combined with fluorine to give you IF7. Come on, write down both the reaction and done in the chat box. Come on, write it down and done in the chat box. Come on, done. Come on, only one done. Acha, write it down. Take your time, write it down. Done. Let us go ahead now. Let us go ahead. Okay. Now, interhalogen compound. Okay, as Sasidaran asked us. Okay. So covalent, they are covalent, they are diamagnetic, they have polarity. Okay. they have polarity because you have a more electronegative halogen. So yes, they are polar in nature. Some of them are polar in nature due to the electronegativity difference. Okay. Physical state is as gases, liquids and solid. We know some of the gases. Yeah, we have seen that in the table. Some of them are gas, some of them are liquid, some of them are solid. Okay, some of them are solid. Now reactivity, similar reactions to those of component halogens, more reactive components except fluorine. Fluorinating agents, so we have IF7, we have the reaction of that. Look over here. So your F can be used as a fluorinating agent. Okay, we can use them as fluorinating agents. Now what do we mean by fluorinating agent? That means we will react it with metals and we will fluorinate the metal. We will fluorinate the metal. Especially look at this reaction, this uranium. Okay, we can react it with uranium. Okay, this we can react it. This is actually used in our nuclear reactors. Okay, this is actually used in the nuclear reactors. Yeah, nuclear reactions is very like uh, is a very interesting topic. Very interesting topic. The nuclear chemistry, the nuclear physics and nuclear chemistry. Yeah, very interesting. If we want to make a career, we have like it is on the boom also now. Yeah, isn't it? You can be a great scientist in that. How many of you have seen Oppenheimer? Anyone? Anyone seen the Oppenheimer movie? No one? But if I ask, how many of you have seen Jailer movie? Hmm. Then everyone, yeah? Isn't it? No? Oh my god, we do not watch movies. Okay. Anyways, so where were we? We can use this fluorides as fluorinating agents. We can use them as a fluorinating agent. For example, W. Which element is this? Yeah? Which element is this W? Tungsten, is it? What is W? Prashansky and Sarjana. What is W? Ragul, Bhuvaneshwari. What is W? Kirtini. W is tungsten. Okay, W is tungsten. Okay, not tungsten, it is tungsten. Okay, Bhuvaneshwari, it is tungsten. So it is a fluorinating agent. W is a tungsten. It will fluorinate the tungsten to give fluoride. Similarly, selenium, it will react with it, will give you fluoride. Again, manganese oxide, sorry. So again, what will happen? Yes, it will fluorinate the magnesium also. It will fluorinate the uranium also. It will fluorinate the silver also. So basically, all your interhalogen compounds, the fluorinating compounds, we can use them as a fluorinating agent. Okay, we can use them as a fluorinating agent. And this is important. Your ClF3 and BrF3 are used for the production of UF6. Okay, it is used for the production of UF6. Come on, write down at least this last reaction. Uranium reacting with ClF3 to give you UF6. To give you UF6. Come on, write it down. UF6. Write down the last reaction and write down this statement also. Okay, ClF3 from this to this. Come on, write it down and done in the chat box. Come on, write it down and done in the chat box. ClF3 or BrF3 are used in the production of UF6. Yeah. let us go ahead. Yes, Sarjana is done, Anne is done, everyone is done. Prashanti, Ragul, Kirtini, Sasidaran. Okay, sure. Let us go ahead. Now, as I told you, hydrolysis, yes, if you hydrolyze them, what will happen? Yes, you will get the hydrolysis compound. Yes, it will undergo hydrolysis. It will undergo hydrolysis. Now, as I told you, the smaller atom, which is more electronegative atom, is generally negative. Over here, it should be X. Okay. So that smaller atom will go with the H plus. Yeah, the smaller atom which is more electronegative. Yeah, it is logical, isn't it? It is logical. It is logical. The smaller atom is more electronegative. More electronegative will go to H plus. Yeah, because it is more negative. Simple as that. Yeah. So for example, if I have ICl and if I have H2O, if I add ICl in water, what will happen? I have I plus I and I have Cl. Correct. I plus Cl minus. You can say it like that. Cl is more electronegative. I have H plus and OH minus. So obviously, what will happen? H plus will go to HCl. OH will go to I. So I will get HOI and HCl. Is it clear, everyone? Come on, write down this reaction, both the reaction for the hydrolysis. Come on, write it down. So more electronegative element will go to H plus. Yeah. So all of them can undergo hydrolysis. Yeah. All of them can undergo hydrolysis. Okay. All of them undergo hydrolysis. Come on, write it down and done in the chat box. Sounds nice. Done. Come on, write it down and done in the chat box.
Sir,
Yes, Sashikaran.
uh, like the the interhalogen compound of XX dash you told, yeah, IF, sir.
Hmm.
Iodine fluoride, you said. Will it
Hmm.
undergo hydrolysis, sir?
Iodine fluoride, to be honest, does not exist in it. Okay, iodine fluoride has a very short half life. Okay, if you notice over there also when we write IF, okay, when we have written IF over there, where did that table go? Okay, over there was a star on it. Huh? Okay, there was a star on it. Okay,
Yes,
so IF, why it does not, like why it is so unstable? First is due to size and due to electronegativity difference. Chlorine is highly electronegative. Iodine is, yes, electronegative, but as not as your fluorine. Okay, so yes, it can undergo hydrolysis, but it is so unstable that it is very hard to detect it. Okay, but logically thinking, yes, it can undergo hydrolysis.
same in the case for IF3 also, sir.
Yeah, same thing. And even IF3, okay, as I told you, see, IF7 is stable. IF7, due to more number of fluorines, it is becoming stable. Okay, but IF and IF3, okay, they are unstable and they have a very short half-life. Okay, they have very short half-life. Okay, but yes, it can undergo hydrolysis. It can undergo
Yes,
hydrolysis.
sir. Sir, in case of ICL, what is that alpha form and beta form, sir?
Which one?
Iodine chloride.
This one. Okay. See, have you heard about your morphism? Yeah, allotropes.
Yes, sir.
What are allotropes?
Uh, Sir, they are like molecularly same but structurally different.
Okay, yeah, you can say that. See, what happens is you have more than one form of compounds. Okay, allotropes, for example, we had studied sulfur. Okay, everyone, we have studied sulfur. We have studied the allotropes of sulfur. We have studied the allotropes of phosphorus. Yeah, red, black, and which one was the other one? And yeah, three types of phosphorus we have studied. Sarjana, what were those? Red, black,
White.
and white. Correct. So similarly, even your ICl, okay, even your iodine chloride also shows your What I was saying.
Allotropy.
Allotropy. Okay, even your ICL shows allotropy. So we have two form of ICL. One is alpha form, one is a beta form. So in that also, alpha form is red in color and your beta form is brownish red in color. So alpha and beta are the allotropes of ICL. Okay.
Sir, as in the case of phosphorus, the heat like given to it determines the
Exactly.
color. So here, which color?
Same thing. Alpha is more stable as you heat it. Okay. Now I do not remember the exact temperature, but if you heat it, it will go above that temperature. It will convert into beta. Exactly same thing.
Okay, sir.
Where were we? Huh. So hydrolysis is done. Next we have now ionization. Yes, they can undergo ionization. Some are partially ionized, some are fully ionized. Then reaction with alkali metals. Yeah, they form salts, they form complex. They form complex. For example, if I react ICL and KCl, if I react ICL and KCl, what will happen? The Cl minus will get added. Same thing over here, ICl3. If I react with KCl, again Cl minus will get added. Yeah, same thing over here, CSF, CSF, that is a cesium fluoride. What is happening? You are getting a complex form, correct? You are getting a positive K plus and ICl2 minus. Okay, ICl2 minus. Is it clear, everyone? So if you react it with metal halides, you will get the complex formation. Okay, you get the ions. Come on, write down this two reaction at least. Come on, write it down, everyone, and done in the chart box. Reaction with alkali metal halides. Reaction with alkali metal halides. Write it down. Reaction with alkali metal halides. Come on, write it down and done in the chat box. Write it down and done in the chat box. Done, done, done. Can we go ahead? Now, these are the strong oxidizing agents, the thermal stability. Okay. Now look at this. This is what I was telling you, electronegativity difference. Yeah. Obviously, as the electronegativity difference will increase, the polarity will increase. Yes, the compounds will break down faster. The compounds will break down faster. So you can write down about thermal stability. Yes, you can write down on the thermal stability based on their electronegativity difference. Correct? So as the electronegativity difference decreases, polarity decreases, the repulsion decreases, the thermal stability, the thermal difference, the thermal stability, what will happen? Yes, it will become stronger. Yeah, it will become stronger. Like for example, the thermal stability decreases as the electronegativity difference decreases. So IF7, okay, what will be the thermal stability? Will it be stable or will it be unstable? Yeah, IF7. Thermally, will it be stable or unstable? Yes, everyone. IF7. Thermally, will it be stable or will it be unstable? Yeah, electronegativity difference is high. More positive, negative, more repulsion. So will it separate easily or will it not separate easily? Will it separate easily or it will not separate easily? What do you think? You think you are tired? I agree. P block is tiring. Yeah, all theory. I agree. Yeah, P block is tiring, but hardly two more lectures. Okay, then two or three more. Two or three more. Okay, then we will be done with our P block. Okay. So over here, look at the electronegativity difference. If electronegativity difference increases, that means there is more positive negative. Yeah. So what is happening? This will separate. Okay, so remember, if it can separate easily, that means thermal stability is low. The thermal stability is low. It will separate easily. Thermal stability means what, Prashanti? If I give the heat, how better does it separate? If it separates easily, thermal stability is low. If it does not separate easily, thermal stability is high. You require more heat energy to separate them. Okay, so write this down. IF, thermal stability very low, then BRF, then CLF. Yeah, write down the thermal stability. Write down the thermal stability. Okay, write down the thermal stability. Thermal stability. Thermal stability. Come on, write it down. Opposite order of your electronegativity difference. Opposite order of your electronegativity difference. Write it down and done in the chat box. Okay. Now let us come to VSCPR. Again, we have come to VSCPR. Huh? Again, like we have already done twice in a booster batch, then twice in the P block. So VSCPR, again I repeat, important. Okay, so VSCPR tells us about the shape and the hybridization of our molecule. So all our interhalogen compounds, yes, all our interhalogen compounds, we will look at the VSCPR of this. Okay, all the interhalogen compounds. Okay, for example, BRF5. Okay, BRF5. Come on, tell me, we have done VSCPR. Okay, tell me how many bond pairs I have, how many lone pairs I have. Those who can solve it, please solve it. And what is the hybridization? Yes, Sasidaran and Sajna, Prashansky, come on, solve it. How many bond pair, lone pair, what will be the hybridization, and what will be the geometry? Come on, go ahead. Solve it properly. Solve it properly on the paper. Come on, and turn on your cameras also. Kirtini. Solve the VSCPR. Come on. How many bond pairs we have? How many lone pairs we have? Come on. How many bond pairs, how many lone pairs, and what is the hybridization? Okay, very good. And what is the geometry for that? Yes, Sasidaran, Prashansky, Kirtini, Sarjna, Ragul. Kirtini, am I audible to you? Kirtini, Kirtini. Sadhana. I'm asking about geometry and not a shape. Kirtini. Kirtini has turned on the camera and she was enjoying on her cell phone. Oh my god. Kirtini. Let me write down her name. Am I audible, Kirtini?
Yes, sir.
What happened? What are you doing? I could see cell phone in your hand. We are in the class, no, hardly 15 minutes are left. Yeah? Come on, keep down your cell phone. Concentrate in the class. Not a good thing. Correct? It is like a disrespect. Okay? So do not do it again. Okay. So how to solve it? Br. How many valence electrons we have? Sashidharan, in the Br, how many valence electrons we have? 5. Is it? No. We have 7. Okay, so look over here. How to solve it? Those who do not know, Prashansi, look over here. How to solve it? BrF5. Okay, I have 7 valence electrons. So I'll draw the 7 valence electron. I'll draw it over here. Okay, I'll draw the 7 valence electron. 1, 2, 3, 4, 5, 6, 7. Correct? Then I'll draw the bonds with it. How many fluorine I have? I have 5 fluorine. So each bond with the fluorine, 1, 2, 3, 4, 5. Correct? Then the remaining Sashidharan is nothing but your lone pair. So I have 1, 2, 3, 4, 5 bond pairs and I have 1 lone pair. So I have 5 bond pair, I have 1 lone pair. So 5 bond pair, 1 lone pair means what? The number is 6. Correct? So 6 stands for over here 6. Sarjana, how sp4 is not possible? Understand this. S can be maximum 1, p there are maximum 3 orbitals, d there are maximum 5 orbitals. Correct? So it is s, p, 3, the number becomes 4 and 2 more, it is d2. Are you getting it, Sajna? Okay. sp3d2. And what is the geometry for sp3d2? And square pyramidal becomes shape. It is not a geometry. sp3d2. What is the geometry for this? Yes, come on, it is common one. sp3d2. What is the geometry? What is the geometry for sp3d2? Sashidharan, Sajna, and Prashanti, Ragul. What is the geometry for sp3d2? It is octahedral. It is octahedral. Now remember this rule. Remember this rule. Octahedral. Okay. We have two types. One is okay. sp3d2 is octahedral. Okay. Now when we have sp3d, okay, that is trigonal bipyramidal. Understand this. I am telling you trick to remember the shape. Geometry is different. Shape is different. Okay. In the shape we do not write the lone pair. Okay. So octahedral and TBP. Okay, remember this, very important. Okay, so octahedral means what? I have a metal, I have an atom over here. We have Br. Correct? We had done for BrF5, isn't it? BrF5. Correct? So I will have F, 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 F. Okay, F, F, F. Then I will have one remaining F over here and one lone pair over here. Okay, so that makes it octahedral. Okay, if I join this, look at this. This is my octahedral. Okay, this is my octahedral. If I join this, this is my octahedral. Okay, and for the shape, we do not consider the lone pair. So it becomes square pyramidal. Your BrF4 is a square. If I join this, this becomes a pyramid. This becomes a pyramid. Okay, so square pyramidal. Now remember this. Remember this. whenever we write down the TBP, let us say I am just giving a hypothetical example to understand this. Okay, if I have BrF5 in TBP, okay, or let us say BrF4 in TBP, does not exist. I am just giving you understand the hypothetical example. Okay, so how will I draw TBP? In the TBP, first thing, the electronegative elements I'll draw on the axial lines. Okay, in the TBP I'll draw it on the axial line like F, F, then I'll go over here F, F, and maybe a lone pair over here. Okay, this is how I will draw TBP. But in the octahedral, first I'll draw the electronegative elements on the equatorial bond. So remember, write it down. In the octahedral, first we draw elements on the equatorial, then we go on axial. Okay, but in TBP, first we write it on axial, then we go on the equatorial. Come on, write it down. That will help you in remembering the shape. Okay, that will help you in remembering the shape. Come on, write it down. Okay, now I3 minus. Okay, we have done it, but I am giving you again. I3 minus, similarly, find it out. Sashidharan, Sarjana, Prashanti, and how many bond pair, lone pair we have? I3 minus. And what is the hybridization? What is the hybridization that you are getting? Come on, I3 minus. I3 minus. I3 minus. Come on, solve it. How many bond pair, lone pair, and hybridization? What is how many bond pairs we have? How many lone pairs we have? And what is the hybridization? Okay. And lone pairs. Okay, you have told me lone pair electrons. Okay. We do not count each electron as a lone pair. Yeah, I am talking about pair. Two electrons will make a single pair. Yeah, like over here BrF5 we have done it, no? Two electron makes a single pair. Yeah. So how can we have 9 lone pair? No. Okay, very good, Sashidharan. I am just talking about the central atom, not the total lone pairs. I am talking about the central atom. Achha, we count it for all. But for VSEPR only we need the central atom, no? We do not require the others. For VSEPR, we need only the central atom, not the others. Okay? And what will be hybridization? What will be the hybridization? Everyone? Yes, you are correct, Sashidharan. What will be the hybridization? sp3d. Okay. Now, sp3d, the geometry is trigonal bipyramidal. Now, apply our rule and tell me the shape. Now, you will understand why this rule I have told you is important. If it is TBP, apply our rule and tell me the shape. Apply our rule and tell me the shape. So those who have not got it, calculate it. You will get it as sp3d or I3 minus. Now apply our rule of TBP. First elements where we will draw and tell me the shape of I3 minus. Yes, Sashidharan, apply the rule and apply the rule. Apply our rule. Perfect. Yeah. Now understood how the shape you will remember. You do not have to by heart it. You do not have to by heart it. Sashidharan, what will be the shape? Yes, Prashanti. Sarjana, what will be the shape? Apply this TBP rule. I told you no. You have written it down in the book also. What will be the shape? Yeah, in this we have 2 bond pairs and 3 lone pairs. 2 bond pairs plus 3 lone pairs. Sasidaran, what will be the shape? Come on, think about it. Yeah, apply our rule of TBP. What did I tell you? In the TBP, first you'll draw it on the axial bond. So if I have I in the center, first I'll draw it I over here, then I over here, and your 3 lone pairs will come over here. Lone pair 1, lone pair 2, lone pair 2. So this is my TBP. So my shape is linear. I'll erase this lone pairs. My shape is linear. Is it clear, everyone, how to get the shape? Yes? Sashidaran, is it clear? Kirtini, Sarjana, is it clear how to understand the shape? You do not have to by heart it. If you apply this rule, you will get it. Okay? So, in the next, you will find this you have to solve. Over here, I have given it via VBT. At home, you have to solve it via VSCPR and you have to check. Okay, all the elements ClF3 important. Okay, it is important. IF5. Okay, IF7. Okay, ICl2 minus. Okay, ICl4 minus. I2 minus. It is I3 minus. We have seen this. Yeah, this is the shape. That is why it is linear. Okay, so all this I5 minus, you have to solve the VSCPR of this. Is it clear, everyone? Okay.